assume we've begun. Yep. All right, so we have Bill. Riley. Ashley. Liv. Angel. Gabby. Caroline. Amelia. The few, the proud. Any questions?
I have your question.
Yes.
Master said chapter 7.
Yes.
10, number 10.
One dimensional problem, two boxes centered towards each other. Box A has a mass of 20 kilo, so velocity B. Yes. That's how to do it. All right, first off, you probably should confirm that momentum is conserved. So what type of collision comes down to the kinetic energy? So you have to look at the total kinetic energy beforehand and afterwards. So if the initial kinetic energy equals the final kinetic energy, and back up for just a second here, the initial kinetic energy would be the kinetic energy initially of mass 1 plus the kinetic energy of mass 2. Don't add the masses and then multiply just some bizarre concoction of the speeds. You do 1/2 mv squared for one mass, 1/2 mv squared for the other mass, add them. Same with one. So if Ki is Kf, if we have the exact same amount of kinetic energy in both cases, then that is the perfectly elastic collision. If Ki is less than, if Ki is greater than Kf, in other words, we lost some kinetic energy, then, and they don't stick together, then that is the imperfect. If there's a loss and they stick together, then that is the perfectly inelastic. And you can tell if they stick together or not. If they have the same final velocity, they have stuck together. If they don't have the same final velocity, they have not stuck together.
Okay.
And then the fourth case is if we gained energy, so the initial kinetic energy is less than what I end up with. This is what I refer to in the video as Lubboresque. What textbooks would consider impossible.
Yeah.
Because I think I gave you the masses, I gave you both velocities before, both velocities afterwards, so, yeah. Is that sufficient for you to tackle the problem?
Yes.
Okay. Go ahead.
I have a question for number 9. It was just, can I see your number 9 first?
Number 9, the one-dimensional problem. Two boxes headed towards each other. Box A has a mass of that, initial velocity. I gave you that. Perfectly elastic, how much kinetic energy was lost? Okay.
So my question is, Mike showed me, he said it's your method 3.
Oh.
How to, did I need to do that?
No.
Okay.
No, it's perfectly valid to do that.
Okay.
I think he read the first part of the question, saw perfectly elastic, and then jumped to a conclusion.
Okay.
So, is that just a matter of whether you needed to do that or not?
It is like, how do I solve it without method 3?
What does perfectly elastic mean?
Perfectly elastic equal to 60.
That's more than that. What makes it perfect?
K initial equals K.
So how much kinetic energy was lost?
0.
Okay. Next time you see Mike, give him a look. How dare you?
I was having problems with master stat. Number 5 part E.
Number 5, this is chapter 6.
Yeah.
Okay, so the momentum 1, all right, collision is not perfect. The velocity of A on collision was the velocity of velocity, okay.
So I just have a question, and maybe my thinking behind this is wrong. But does it, the velocity still need to equal the velocity of A?
It just purely conservation momentum, not perfect means
They're like,
we're not in either of these two camps here.
okay.
So it's an imperfect collision. Well, I'm not even asking you whether it's this or this. It's just a straight up, look at the total momentum beforehand. It's got to equal the total afterwards.
Yeah,
I gave you information about one of them, so sort of work it out from there.
okay, that's what I was wondering.
Okay,
Okay,
is that sufficient to get
I
you going?
hope so.
Okay. I can do a similar problem, not that one though.
Of course,
Would you like me to?
I would appreciate it.
Turn this on.
And you don't have to.
So I'll take a 5 kilogram box heading that way at 10 meters per second. I hope these aren't the numbers that are just solid.
Let me, double check. No, it's a 20 kilogram box, and you did use 10, so if you want to change 10.
Yeah, all right, so we'll make it 8. And I'll have this one going that way at,
The one here, you have -5, and then you have 30 kilograms, so that, you
All right.
want to use 30. Just so you know.
we'll make this 2 kilograms. All right, so it's in essence the same type of problem.
Yes,
I presented it differently here, but I gave the picture in terms of direction. I know the 2 kilograms going to the left, the 5 kilograms going to the right.
yes,
In the problem I gave, I actually specifically said one was a positive velocity, one
yes,
was a
you
negative
did,
velocity.
and so I understood that.
All right, so so this is before,
Mhm.
and then after. I gave you one of them, doesn't really matter which one I give.
Yeah,
We'll just say this is bouncing back at 9 meters per second. So, you need to find the total momentum beforehand. All right. The initial momentum would be the initial momentum of the 5 kilogram mass plus the initial momentum of the 2 kilogram mass. I'm hoping you know the formula for momentum. If not, then you probably haven't looked at this stuff yet. What is momentum equal? Open to anybody, just shout it out.
Mass times velocity?
Yep.
Yep.
And so the momentum of that one would be 5 times 8. What's the momentum of this? If that's, the momentum is 40 kilogram meters per second, what's the momentum of this?
So it should be negative?
Yes, and that's a key thing there, minus 22. And so we end up with 18 kilogram meters per second, or Newton seconds, or if you created your own, whatever that is. What's my total final momentum?
At 18.
Sorry?
Isn't it 18?
Yes, it'd be the same.
That's what I thought. That's, I'm on the right track.
Okay.
That's exactly, oh, but when we go here and you change it, I guess my question is, does it still need to equal 18?
Yeah, the total is still 18. We have this, so we have this mystery here, this momentum final, plus I got my 2 kilogram doing something of this momentum final. Those have to add up to be 18.
That's what I thought. Okay, I got it right.
You
That's
good?
what I thought. I just was
Okay.
triple checking.
I'm getting the hint that you want me to stop.
No, you can keep going. It might help.
Genesis?
Yeah, so I'm going back to 10. I have to do K initial plus K initial for both. And then I have to do the same for the final, right?
All right, why don't we just use this problem right here,
Okay.
and we'll kill both birds. All right, so what is this momentum after the collision? That's a 5 kilogram mass, 9 meters per second to the left. Say it again?
45.
What?
The momentum of this mass after the collision?
Isn't it negative?
Yes, negative 45. So negative 45 plus whatever that momentum is equal to 18. So the final momentum of the 2 kilogram mass has to be, well,
18.
whatever I can add to 45 to get 18, which is 63 kilogram meters per second. That's equal to the mass times the velocity. And so therefore 2 times the final velocity is going to be equal to 63. And we end up with the final velocity for the 2 kilogram mass to be 31.5 meters per second. I will tell you, this is a flubber-esque problem, but go through the process. Questions about how we got that? All right, so the total kinetic energy initially is, well, the total kinetic energy of the first object plus the total kinetic energy of the second object. I'm using 5 and 2 just to represent, because those are the masses and it helps me keep track. If you'd rather do 1 and 2 or A and B, sure. So for the first one, well, all of you know the formula for kinetic energy, so I'm about to ask it. So just prepare yourselves. Since no one's looking through papers, I'm assuming everyone knows it then. You need a moment. Nope, you're good to go.
Which question are you going over again?
That was related to the last problem on the chapter 6 master set. This is related, I'm now gonna use that example to talk about the last problem on the chapter 7 master set.
Okay, yeah, that's what I was gonna ask next first.
Okay. All right, hey, what's the formula for kinetic energy?
1/2 mv squared.
Enthusiasm too. Maybe not, Gabby. Was there enthusiasm there? So I have 1/2 times the mass of the 5 kilogram times the speed of 5 kilograms squared plus 1/2 times the mass of the 2 kilogram times the speed of the 2 kilograms squared. But we're just doing the initial stuff, so I got 1/2 times 5 times, I think I had 8 squared, plus 1/2 times 2 times 11 squared. Why not a negative 11 squared?
Because if you square a negative, it's one positive.
Okay, you could look at it that way. There's a more picky answer to it. I squared the negative 11 for years, then later realized the negative actually should not be there.
Oh, is it because it's not a vector?
Right. It is just speed. The negative is an indication of direction, and there is no direction here. So we end up with whatever that is. So it's 64 divided by 2 is 32 times 5 has 0. 160. So this is what I'm getting, that there could be a careless error in there easily. Okay, I think that was a nod. Okay. Units? Yes. So I have 281 joules of energy. And now I just need to figure out what my final kinetic is. So I'm gonna do the exact same thing, except I have different final speeds. So I'm gonna have for final 1/2 times 5 times 9 squared plus 1/2 times 2 times 31.5 squared. Which is, if someone would be kind enough,
The first part is 202.5.
is what again?
202.5.
202.5?
The second part is 992.25.
992, 25. And therefore the sum
$1,194.
So we go from 281 joules to 1,194.75 joules. So which scenario is it?
It's, F.
Flubber-esque?
Yes.
Okay. Or impossible, depending upon the textbook or the instructor.
You said that's when the final it's more?
Yes. The only way you can gain kinetic energy naturally is if you have some sort of additional, in essence, an explosion. You need some way of creating this energy. So
So you said
fireworks can gain kinetic energy, but that's only because there's an explosive.
the type of collision is, you said flubber-esque? What'd you say?
Flubber-esque.
Oh.
I use that term, assuming you've seen at least The Absent-Minded Professor or Flubber. If you have not seen either of those films, then I guess Flubber-esque is a brand new word for you.
So, you took out the negative with the negative 11. would you take out the negative for the ones in the problem?
If I'm finding kinetic energy, it's 1/2 times the mass times the speed squared. The negative is directional. I need the negative in there when I'm dealing with momentum, because that is a vector. But energy is a scalar. Also, if you put the negative 11 in there and squared it, you'd get a positive number.
Right, okay.
That's Johnny.
I have a question about number 4 on the chapter 7 set.
On number 7 or 6?
7.
7, okay, thank you. Man pushing a box. Okay,
So explain the scenario that would cause this. Like, what are you like looking for?
if I have a box that is moving 10 meters, which way would he push on it in order to get the most amount of work? And which way would he push on it to get the least amount of work? That's what that in essence is what I'm looking for.
So you're just looking for like a left, like, are you looking for like a direction or like a positive or negative answer?
Looking for force, move 10 meters. No, I actually am looking for a number. So give me the scenario and tell me what the number is.
It says he pushes on a box with a constant 50 newtons of force while the box moves 10 meters.
Right.
And then what was the most amount of work? Or what are you asking? I'm confused.
The most amount of work. So how do I get the most work? How do I do the most work on an object if I'm pushing on it?
The net force and the displacement?
Now looking at just what he's doing. I'm not worrying about any other forces acting on it. This is the work that he is performing.
Exactly what he's doing.
Pardon?